there everyone, welcome back to the channel. I'm the GCSE science teacher, and in today's video we're going to be talking about cracking and alkenes. This is part of the organic chemistry topic for GCSE chemistry students. So if you have stumbled across my videos for the first time, hello and welcome. Please do feel free to subscribe, join our community, and also if you do enjoy the video, give it a big thumbs up so I can tell I should make more of these sorts of videos for you guys. But also if you would like to, feel free to share it with someone else so they also can benefit from learning more. So let's get started. First of all, let's remind ourselves when we talk about alkenes, we're talking about a family of hydrocarbons. And a hydrocarbon, remember, is a molecule that contains only hydrogen and carbon. It's part of a homologous series, and this is because alkenes have the same general formula, which is CnH2n. Remember, alkanes, which we talked about previously, and I'll link that video for you, they had the same general formula, which was CnH2n plus 2. So in the exam, they could ask you some differences or similarities between the two types of homologous series. Just be aware of that general formula for alkanes versus alkenes. Remember as well, because they are part of the same homologous series, alkenes have a functional group which is the same in each case. So it's a double carbon bond. Remember, carbon can only make four covalent bonds. And remember, covalent bonds are a shared pair of electrons between two nonmetals. In the case of an alkene, remember, two of those bonds are given to another carbon atom. So in this case, you're only left with, or the carbon's only left with, two other bonds to form covalent bonds with other atoms. So that's one of the differences there between alkanes and alkenes as well. Because it has the double carbon bond, we call this an unsaturated hydrocarbon. And because of the double bond, we can actually test for this and we can see if something is an alkene. And we do this by using a solution called bromine water. And this has kind of like an orangey brown color. But if we place an alkene within there, it actually decolorizes. You never really want to say it goes clear, because actually bromine water is clear. It just has a kind of a brownish orange tinge to it. You can see through it. It's just that there's no color anymore when there are alkenes present. So be very careful to use the word decolorizes in your answer. A couple of other things to mention as well. At GCSE, you really only need to know about the key alkenes. So you need to know about ethene, which has two carbons. You need to know about propene, which has 3, and butene, which has 4 carbons. Notice there's no methane. There's no such thing as that, because in the case of alkanes, we know that there's methane, which had 1 carbon atom at its center. But because of the carbon-carbon double bond, you need at least 2 carbon atoms, which is why there is no methane that could possibly exist, because there's only 1 carbon in the case of meth. That's what METH, that prefix means. That just means 1 carbon. And in the case of alkenes, you actually need 2 carbons for that double bond to form. Okay, so just as a bit of a summary then, just to kind of clarify our understanding, alkanes versus alkenes and some of the similarities in between. This is what we call a Venn diagram. On the left, we have the information about alkanes. So they're less reactive, they're used for fuels, and this is because they actually are very flammable. They also can have quite a good viscosity, so they can be used for things like petrol and diesel. Bromine water stays brown or orange if there are alkanes present. And remember, this is a saturated carbon bond which forms, so it's just a single carbon covalent bond that forms. However, in the case of alkenes, they are much more reactive. They decolorize bromine water, which is a test for it. They have that double unsaturated carbon bond, which forms between carbon atoms, which is covalent, and they can be used to make polymers and plastics. So there's different uses for each. Remember, you will find both of them in substances that contain hydrocarbons, because both of them are hydrocarbons. So they have carbon and hydrogen within their structure. They can be used for fuels. They can be used for combustion, so we can burn them to release energy in the case of fuels as well, but some are better than others. Like I said, viscosity, they kind of vary on their viscosity depending on their chain length, and again with their flammability. I've written at the bottom chains and in brackets BP. So each of them will have a chain length. The shorter the chain length, the smaller the molecule is, the lower the boiling point is. And that was kind of something that we discussed during my previous video on this topic about fractional distillation. Again, I'll link it for you if you missed it. But essentially, the smaller the molecule is, the less intermolecular forces there are to break, and that's why the boiling point is lower than those longer chain hydrocarbons. So how do we go from alkanes to cracking? What's cracking? Why is this relevant? Because you may have heard of the word cracking. Maybe it's Easter recently. You may have heard about cracking Easter eggs. Who knows? But cracking in chemistry is actually a really important process, which basically gets hydrocarbons and breaks them down or cracks them into smaller, more useful molecules. And we do this in two different ways. We can use either catalytic cracking or steam cracking. And both of them are very good at just breaking down large hydrocarbons, those long chain hydrocarbons that have very high boiling points. We can break them down into more useful fractions. So for example, if we use catalytic cracking, you need to know some of the key conditions that these processes undergo. So catalytic cracking, as the word may suggest, it will contain a catalyst. And just as a bit of a recap on what a catalyst is essentially a chemical or a substance which does not get used up during a chemical reaction, but it lowers the activation energy, meaning that more collisions can happen more frequently, and therefore the reaction can occur at a much quicker rate. And this is really useful because sometimes in industry, we use a catalyst to actually bring down the overall cost of, say, energy. If the temperature is very high, it requires a lot more energy, and that can be very costly. So therefore, using a catalyst that can be used over and over and over again, that actually makes the industrial process much more affordable in the long term. So catalytic cracking essentially needs a catalyst, and the catalyst you need to know is called zeolite. This is essentially something that's made up of aluminium oxide and silicon oxide, and it needs a high temperature of 550 degrees. However, this is much lower in temperature because of that catalyst, because steam cracking is another version that we could use to break down those hydrocarbons into much smaller fractions. And instead, it actually requires a much higher temperature, over 800 degrees Celsius, which is extremely costly. So there's kind of two different ways we can actually break down those hydrocarbons into more useful molecules, in separate ways, of course, as well. The products of cracking. So you need to be aware that when we crack a larger hydrocarbon, say, for example, hexane, the products are always going to be an alkane, which is much smaller, and an alkene as well, which again is much smaller. But remember, whenever we look at reactions, notice the number of carbons and hydrogens on either side of the arrow, or the reactants and products. They need to be in a ratio that is equal. Remember, we can't just create atoms out of nothing, or we can't lose atoms. So you could get asked to balance this equation in both cases. In the case of hexane being cracked into butane and ethene, you can see butane has 4 carbons. You can see ethene has 2 carbons. The difference here is this particular example is already balanced. You can see the number of carbons on either side of the arrow equal the same amount, same with the hydrogens. But just be careful in the exam, they could ask you to do that. If you would, by the way, like a video on balancing equations, I'm more than happy to do that, because I think it will kind of require an entire video on its own. A lot of students struggle with it. So if you would like that, just let me know in the comments or give this video a thumbs up. I'm more than happy to do that. But just overall then, why is cracking done? Why are we breaking down those hydrocarbons into shorter, smaller ones? And it's essentially supply and demand in industry, in business, in, buying and selling of things. If there's a higher demand for fuels that are much smaller in chain length, like petrol, for example, they will obviously be more coveted. People will want them more and therefore pay a better price. So that's kind of why cracking as a process to break down those larger hydrocarbons, it's kind of used in the meantime to kind of make those smaller hydrocarbon chains available and therefore more useful, and therefore we can actually profit from them as well. And that's it from me today. I've been the GCSE science teacher, and you have been curious. If you did enjoy the video, please give it a big thumbs up, share this with someone else, and do subscribe if you haven't already. Lots of you are watching my videos, but some of you are not yet subscribed. So please do consider doing that. It'd be lovely to have you as part of our community. In the meantime, if you want more support with biology, chemistry, or physics GCSE revision, check out the playlist that I've linked for you, and also my Instagram and TikTok, where I do post some key information on there as well. Have a great day, and I will catch you in the next one. Bye.